Wolf-Rayet 124, a star in transition. The rare sight of a Wolf-Rayet star, among the most luminous, most massive, and most briefly detectable stars known, was one of the first observations made by NASA's James Webb Space Telescope in June 2022. Webb shows the star, WR-124, in unprecedented detail with its powerful infrared instruments. The star is 15,000 light-years away in the constellation Sagitta. Wolf-Rayet stars are a rare prelude to the famous final act of massive stars, the supernova. In one of its first observations, NASA's James Webb Space Telescope captured the Wolf-Rayet star WR-124 in unprecedented detail. A distinctive halo of gas and dust frames the star and glows in the infrared light detected by Webb, displaying knotty structure and a history of episodic ejections. Despite being the scene of an impending stellar death, astronomers also look to Wolf-Rayet stars for insight into new beginnings. Cosmic dust is forming in the turbulent nebulas surrounding these types of stars, which is composed of the heavy element building blocks of the modern universe, including life on Earth. Massive stars race through their life cycles, and only some of them go through a brief Wolf-Rayet phase before going supernova, making Webb's detailed observations of this rare phase valuable to astronomers. Wolf-Rayet stars are in the process of casting off their outer layers, resulting in their characteristic halos of gas and dust. The star WR-124 is 30 times the mass of the Sun and has shed 10 suns worth of material so far. As the ejected gas moves away from the star and cools, cosmic dust forms and glows in the infrared light detectable by Webb. The origin of cosmic dust that can survive a supernova blast and contribute to the universe's overall dust budget is of great interest to astronomers for multiple reasons. Dust is integral to the workings of the universe. It shelters forming stars, gathers together to help form planets, and serves as a platform for molecules to form and clump together, including the building blocks of life on Earth. Despite the many essential roles that dust plays, there is still more dust in the universe than astronomers' current dust formation theories can explain. The universe is operating with a dust budget surplus. Webb opens up new possibilities for studying details in cosmic dust, which is best observed in infrared wavelengths of light. Webb's near-infrared camera balances the brightness of WR-124's stellar core and the knotty details in the fainter surrounding gas. The telescope's mid-infrared instrument, MIRI, reveals the clumpy structure of the gas and dust nebula of the ejected material now surrounding the star. Before Webb, dust-loving astronomers simply did not have enough detailed information to explore questions of dust production in environments like WR-124, and whether the dust grains were large and bountiful enough to survive the supernova and become a significant contribution to the overall dust budget. Now those questions can be investigated with real data. Stars like WR-124 also serve as an analog to help astronomers understand a crucial period in the early history of the universe. Similar dying stars first seeded the young universe with heavy elements forged in their cores, elements that are now common in the current era, including on Earth. The luminous, hot star Wolf-Rayet 124, WR-124, is prominent at the center of the James Webb Space Telescope's composite image combining near-infrared and mid-infrared wavelengths of light. The star displays the characteristic diffraction spikes of Webb's near-infrared camera, NIRCam, caused by the physical structure of the telescope itself. NIRCam effectively balances the brightness of the star with the fainter gas and dust surrounding it, while Webb's mid-infrared instrument, MIRI, reveals the nebula's structure. Background stars and background galaxies populate the field of view and peek through the nebula of gas and dust that has been ejected from the aging massive star to span 10 light-years across space. A history of the star's past episodes of mass can be read in the nebula's structure. Rather than smooth shells, the nebula is formed from random, asymmetric ejections. Bright clumps of gas and dust appear like tadpoles swimming toward the star, with tails streaming out behind them, blown back by the stellar wind. Wolf-Rayet stars are known to be efficient dust producers, and the mid-infrared instrument, MIRI, on NASA's James Webb Space Telescope shows this to great effect. Cooler cosmic dust glows at the longer mid-infrared wavelengths, displaying the structure of WR124's nebula. The 10 light-years wide nebula is made of material cast off from the aging star in random ejections, and from dust produced in the ensuing turbulence. This brilliant stage of mass loss precedes the star's eventual supernova, when nuclear fusion in its core stops and the pressure of gravity causes it to collapse in on itself and then explode. As MIRI demonstrates here, Webb will help astronomers to explore questions that were previously only left to theory, about how much dust stars like this create before exploding in a supernova, and how much of that dust is large enough to survive the blast and go on to serve as building blocks of future stars, planets, and complex molecules. This composite image of star WR124 captured by the James Webb Space Telescope's near-infrared camera and mid-infrared instrument includes arrows, scale bar, and color key for reference. The north and east compass arrows show the orientation of the image on the sky. Note that the relationship between north and east on the sky, as seen from below, is flipped relative to direction arrows on a map of the ground. The scale bar is labeled in light years, which is the distance that light travels in 1 Earth year. 1 light year is equal to about 5.88 trillion miles or 9.46 trillion kilometers. I hope you found this video interesting. Consider subscribing Explore for more similar contents like this. You might be interested in these videos. I highly recommend you to watch these videos.